we're talking about the quiz that is tomorrow, just Tuesday, December 1st at Mount Lebanon APCS. It's going to be on the same material as the previous quiz, only tomorrow's quiz counts towards the Test 3 grade. To remind you from a previous Piazza post, you need to know all of this for tomorrow. You need to know about merge from mergesort, insertion and selection sorts, both searches, which we'll talk about in a moment, and our code from sorts.java. You're going to use part of today in class to review this, in particular, of course, this video, but also there's some discussion you can have afterwards. If you look here in the appendix, you will see here's the computer science course description, and if you search, for instance, for sequential search, you can see Appendix C. That's the one we care about. And here we go. Here's Appendix C, and these are the algorithms you need to know. Let's talk about search to begin with. Sequential search, I think most people call linear search. I certainly call it linear search. But sequential search, you're searching one element after another. You're given an array of elements. You're given a target or a value, and you're asking, is this target inside this array? For sequential search, we are assuming that this array is not sorted. If it is sorted, we'll use binary search, we'll talk about in a moment. Sequential search is straightforward. Oops, pardon me. Oh, that was nice. Sequential search, let me find it. Sequential search is straightforward. You simply iterate through every element, every index, and check if the element at that index is the target. And if so, you return the index. This is a pretty standard way when you're trying to find an element. You return the index where it occurs, or -1 if it didn't occur anywhere. Very straightforward. As for the worst case big O, it would be if the target's not in the list or the array. So you have to check all n of them. So this is an order n algorithm. Fine. Of course, you should be able to write this from scratch effortlessly and quickly. Following on with binary search. So binary search, the idea is it's the same problem, only this time the array is actually sorted from least to greatest. In that case, as they say, precondition, elements are sorted in ascending order. In that case, we could be way faster in how we search for this target. For example, if you have an old-fashioned phone book, and it's big, thick phone book, and the names are in alphabetical order, and you're looking for John Doe, you can open the phone book to the middle, and in the middle you might have someone like, I don't know, Joe Smith. Kind of strange to have that in the middle. You think something closer to M, but in this phone book, who cares? It's Joe Smith. That's the middle name. Since John Doe, D, comes before Joe Smith, S, we know that John Doe has to be in the front half of that phone book. And so we can rule out the entire back half of the phone book in one check. That's huge. So, you might have, it's a big phone book. There's 1 million names in it. In one check, we ruled out 500,000 names. And then we proceed in the same way. Now that we know that it's between 0 and the middle, we check the middle of that range. And then we can rule out half of that range. And we keep doing this over and over again, checking the middle value of the range and ruling out half the range on each step. This should feel similar in some regards to what's going on with mergesort, in that the way the number of passes in mergesort is determined. There we keep doubling the size of the list until we get up to n. Here we keep halving n until we get down to 1. Same thing in reverse. In any case, there's log n, log base 2 of n, total number of checks in the worst case. So whereas sequential search is order n, binary search is order log n. And as we know, log n is much, much faster than n. So binary search is for sure preferable. The thing is, you can only use it if the elements are sorted. So you might say, fine, if the elements aren't sorted, sort them and then use binary search. Well, that's not great because sorting is an n log n operation. So if you're only going to do search once or even a small number of times on an unsorted list or array, you should just use sequential search. If you're going to do it many times, or it happens that the array is already sorted, then for sure, you should use binary search. Here's your implementation of binary search. You want to go between the left and the right. That's the smallest index where this target could be, and this is the largest index where the target could be. Initially, it's the left end and the right end of the array. As long as these two haven't crossed, find your middle index, and there's three possibilities. One is that the target is smaller than the middle. So now what you want to do is you want to pull your right end all the way up to the middle. Otherwise, the target's greater than the middle, you pull your left end up to the middle. Otherwise, here, well, we actually found it. We're done. So you return the middle. Remember, you actually, in these algorithms, you return the index where you found it, and middle is an index. And of course, -1 if we didn't find it. There is an important, small but important thing to consider here, and it's this. We don't say right equals middle. We say right equals middle -1. And we don't say left equals middle. We say left equals middle +1. That -1 and +1 turns out to actually be important. First, let's think about why it's there. We know that the target can't be at elements of middle because we tested that directly. It's smaller than elements of middle. Since it can't be at the middle, middle itself is no longer a valid index. So middle -1 would be the rightmost valid index possible. So it makes sense to do -1. Conversely, the +1 for the same reason on the left side. But why is it so critical? And for that, consider if left equaled right. Let's say we winnowed this down to, they're both 3. Left is 3 and right is 3. So they're both at index 3. Okay? So the middle is 3 plus 3 is 6 over 2 is 3. If the target is less than elements of 3, let's say it is, okay? If you set your right just to middle, your right would become 3 again, and we would loop forever. But in this case, we set our right equal to 2, and then when we get back to the top, the right and the left have crossed, and we're done. If you don't do this -1 and +1, you will land in an infinite loop here when left meets right. But by doing the -1 and +1, you are certain that no matter what happens, the range will always get smaller in every pass, and therefore this will terminate. So that's it for binary search. For selection sort, we have seen this. You should be very comfortable with this. You should also be comfortable with replacing these 3 lines of code with a call to a swap method that you write yourself. You should also be comfortable with any variant of this. For example, to do maximum-based selection sort, so you search through and find the maximum index, and you swap out the maximum. The only thing that's different there is you would obviously be swapping to the end and not the beginning. You also have to understand why this is j plus 1 and not just j. Okay, and also why this is elements.length -1 and not just elements.length. These are things that you'll talk about when this video is over. In the insertion sort, you have to know why we're starting at 1 instead of 0, why we're going to length and not length -1, because remember here we went to length -1. There's good answers for all of these questions. And then you have to understand in this while loop what this is doing. Okay, you have to understand what this entire loop is doing. And here's a question for you. Why are there no swaps at all going on here? After all, here, this is how you swap. These 3 lines of code swap. And in insertion sort, we're not swapping. We're definitely moving values around, but not the same way, not swapping. Why not? Okay. Next, for merge sort, you are not responsible for recursive merge sort, and you are not responsible for, in particular, actually, it turns out this is not recursive. It's calling merge sort helper. And merge sort helper, the way they've written it, is recursive. And you can tell because right there, that's the recursive call, and there, that's a recursive call. So this in particular is what you're not responsible for. But we also will have you not responsible for the wrapper that calls it. But you are responsible for their form of merge. And I saw some posts on Piazza asking about their recursive merge. There's nothing at all recursive about this merge. This merge, look, there's nothing in here where it's calling itself. So this merge is not recursive, and you are responsible for it. And our merge sort can use their merge, and we wrote one that way in the sorts.java code. And also I separately wrote a separate merge, which works a little bit differently in subtle ways. I mean, obviously they work basically the same. Remember, every algorithm can have numerous similar but different implementations. In any case, you are absolutely responsible for this, and you're responsible for talking about why our merge that I wrote is different from the merge they wrote, in what ways, and discussing which way is better in your opinion and why. So, oh, look, their merge, of course, continues on. Look at that. But even so, there's still no recursive calls here. Okay, and naturally, you'd have to understand every element, like what's going on right here. That's a good question. What's going on right here? When would we get here? What's going on at this point, in just a few words of English. So be sure you can look at this code and describe algorithmically what's going on at each part of the code. Okay, that's also what you'll talk about when the video is over, which interestingly enough is right now.